Bismillahirrahmanirrahim. The title of this presentation is Crystallographic Point Groups, Space Groups, and their interrelationship. This presentation constitutes an important part of solid-state physics. As I have told you, solid-state physics lies at the heart of material science, whereas crystallography lies at the heart of solid-state physics. And there is no concept of symmetry and crystallography without point groups and space groups. Also, point groups and space groups are inextricably intertwined with each other. So, this is the outline of this presentation. In the first part, I will give you a brief introduction about crystal lattices, unit cells, and their Bravais types. The second part covers description of point groups of 14 Bravais lattices, whereas in the third part, a full description and details will be provided to you related to space groups. And as I stated earlier, space groups and point groups are closely related to each other. There's a close linkage, so we can convert any space group into its corresponding point group. And there is a very simple technique involved in this. And in the final portion, I will give concluding remarks. Unit cell is a very basic term of crystallography, but unfortunately most of the students and even some teachers are baffled. They are confused in the understanding of this term. Unit cell is an area in 2 dimensions and volume in 3 dimensions of any crystal lattice, such that while building up a crystal lattice from these cells, 2 conditions should be fulfilled. If these 2 conditions are satisfied, if they are fulfilled, then that area in 2 dimensions and volume in 3 dimensions should be called a unit cell. The first condition is there should be no void or empty space between 2 consecutive areas or volumes. Okay, and the second condition is there should be no overlapping between these 2 areas or volume. When these 2 conditions are satisfied, then yes, we can call that area in 2 dimensions and volume in 3 dimensions a unit cell. So, keeping in view this definition, we can define infinite number of unit cells in a crystal lattice. Okay, but the question arises, if we can define infinite number of unit cells, then why we stick to a particular unit cell, to a specific unit cell in a crystal lattice? The reason is we should always opt for that unit cell which gives minimum volume and maximum symmetry. These 2 are very important terms. You need to remember that, dear students. Minimum volume and maximum symmetry. So a unit cell should be in true sense a representative of the crystal lattice. So that's why it's written in here, by convention the unit cell is so chosen to have the smallest possible volume while reflecting full symmetry of the lattice. And remember, we can have a primitive unit cell as well, and this primitive unit cell can be derived from any centered unit cell, because in some cases we need a primitive unit cell to describe a crystal lattice in a more simpler way. That's why we need a primitive unit cell. And hopefully you would know what a primitive unit cell is. Now, again, two conditions: minimum volume or minimum area, because we are discussing now three-dimensional crystal lattices, so I will use the term volume. So minimum volume and maximum symmetry. In view of these two conditions, we can define at the most 7 basic crystal systems. The first of them, which is the most deformed unit cell, is triclinic. So for the triclinic structure, as you know, my dear students, that there are 6 parameters on the basis of which we can define a unit cell. So for the triclinic structure, these 6 parameters are A, B, C, which are crystallographic axes, and alpha, beta, and gamma, okay, which are the interaxial angles. So in this case, A is equal not to B is equal not to C, and alpha is equal not to beta is equal not to gamma is equal not to 90 degree. This 90-degree value is very important regarding crystallography. That's why we use 90-degree term, and in some cases 120-degree term. So we have no requirements for the symmetry. We don't have any requirements for the choice of crystallographic axes, and we don't have any choice for interaxial angles. The monoclinic structure is the next one, which is having 1,2f axis of rotation, 1,2-fold axis of rotation, and this axis of rotation is such that it is parallel to the B. In other words, the B axis is always defined with the help of this 2f axis of rotation, okay. So that crystallographic axis will be B axis, okay, the one which is parallel to the 2f axis. And as far as A and C are concerned, they are perpendicular to 2f. As far as the angles are concerned, then alpha and gamma, they are equal to 90 degree, whereas beta is not. Similarly, for the orthorhombic structure, we can have 3 number of 2-fold axes such that they are perpendicular to each other, and A, B, and C lattice parameters, they are parallel to their corresponding 2f axes, and alpha, beta, and gamma, they are 90 degree. Trigonal structure is also called a rhombohedral structure, as having a 1,3f axis that goes straight away through the body central points and giving you a 3/4 axis of symmetry. And in this case, these 3 parameters A, B, and C are equal to each other, As far as angles are concerned, then alpha is equal to beta is equal to gamma. They are not equal to 90 degrees. Okay, I think this should be disconsidered. This has happened mistakenly, so please disconsider this. Ignore this. For the tetragonal structure, we have one fourfold axis of symmetry in the tetragonal structure, and the C axis is such that this is parallel to 4F axis, whereas A and B are perpendicular to 4F. And alpha, beta and gamma angle, they are all equal to 90 degrees. For the hexagonal crystal structure, we have one sixfold axis of symmetry, and C axis is such that it is parallel to sixfold axis of symmetry. A and B are perpendicular to 6F. Remember, my students, we always prefer to mention that axis of symmetry having maximum n value in here. So the maximum value for this hexagonal structure is 6, that's why 6 happens in here. Whereas in the tetragonal structure, the maximum value comes out to be 4, that's why we preferably want to mention this in here. Cubic is the most symmetric and in most of the cases high temperature crystal structure, having 4 3F axes. A, B and C are related by 3F. And alpha, beta and gamma, they are all equal to 90 degrees, and A is equal to B is equal to C. As I told you earlier, we can have a primitive lattice which is defined with the help of a primitive crystal structure, but some of the structures will be the same. The only difference will be their central points. The central points of the similar structure may happen in their face, like the ones in here. Each face contains a central lattice point. That central point may exist in the center of the body, like the one in here. That central point may exist at the two faces, that lie against each other. So as far as the simple cubic structure is concerned, then we can have 3 Bravais lattice types. Okay, so this is the one Bravais lattice. This pronunciation is Bravais, remember, my students, okay, not Bravais. Okay, you need to be careful about that. This is the face-centered cubic structure, and this is the body-centered cubic structure. For the tetragonal crystal structure, we have 2 Bravais lattice types. One is a simple tetragonal, the other one is body-centered tetragonal. The next one is the hexagonal crystal structure. We can have only the primitive crystal structure for the hexagonal. For the simple orthorhombic, we can have all 4 types of Bravais lattices. Simple one, the body-centered, base-centered, and the face-centered. For the rhombohedral crystal structure, we can have only one type, which is the primitive one, whereas for the monoclinic, we can have simple monoclinic, base-centered monoclinic, and finally only one Bravais type for the triclinic structure. Now, coming to symmetry of elements. Symmetry in general is defined as any physical system, any structure, or any function in mathematics that regenerates, that reproduces itself after going through certain transformations, certain operations, certain changes, then that would be called symmetry. So in this case, we will focus only on crystallographic symmetry. Crystallographic symmetry consists of certain operations. Number four, we have translation, we have rotation, we have reflection and inversion. The first two operations, that is translation and rotation, we have subtypes of rotations as 2, 3, 4 or 6-fold symmetry. So translation and rotation constitute first kind of operation. Rest of the two, reflection and inversion, constitute second kind of operation. As far as the translation is concerned, then a simple illustration describing this translation or transformation. If we have a point with coordinates x, y and z, and it translates itself to some other location with coordinates x prime, y prime, z prime. So under this axis system, we can have the final coordinates, and that are described with the help of this transformation vector, which is having components as tx, ty and tz. This is the matrix representation for this transformation. We can have 1, 0, 0 tx, 0, 1, 0 ty, 0, 0, 1 tz, 0, 0, 0, 1. Okay, this is for the completion of symmetry. X, y, z 1, x prime, y prime, z prime 1, and these are the corresponding equations that you can get from multiplying these two matrices and equating them to x prime, y prime, z prime, etc. As far as the rotation is concerned, then for this we have considered a coordinate system having this as x-axis, y-axis, and the z-axis is just towards the reader, towards you. So this is a rotation that's happened along z-axis, but in general a rotation can be along x-axis, y-axis as well. Since this rotation is along z-axis, therefore the matrix representation for this rotation is this. We have to put just the value of theta, and then we can figure out the final coordinates if we know the initial coordinates. Remember, my students, as far as the subtypes are concerned, then for the 2f rotation, as I told you earlier, the value of the angle in degrees is 180 degree, and this is called 2f rotation because doing it twice brings you back to where you started. This is the reason, the physical reason for that. And this is the crystallographic symbol for this 2-4 axis of rotation. Sorry. In here, this is the matrix representation. The first matrix, the second one describing initial coordinates of the point, and the third one lying at the right hand side of the equation, giving you coordinates of the final point. And because the z-axis is unchanged in here, so it means that this rotation is happening along z-axis. This is the 3f rotation. So the angle for this is 120 degrees by figuring by plugging in this 120 degree value in here, we can figure out the final coordinates of the point if we know the initial coordinates. This is the 4F rotation. For the 4F rotation, the value of the angle is 90 degree, and then similar way of description. For the 6F rotation, okay, we can have the value for the angle to be 60 degree, and then the crystallographic symbol. This is the inversion, which is another symmetry element, and of course an important element. This is the corresponding matrix representation. Remember, my students, when a part of the unit cell in a crystal lattice is inverted, then all of the coordinates of that part change their signatures. These are the initial coordinates, these are the final coordinates. So this point differentiates this inversion from reflection. In reflection, you will see now in the next slide, in reflection we have only one coordinate with changed signature. So this is reflection. In here, this reflection has taken place along z-axis. It means that the mirror plane lies perpendicular to the z-axis. This is the glide plane. Glide means the combination, and from this point on, okay, we will discuss combined symmetry operations. Remember, my students. So this is combined symmetry operations. This is a symmetry operation that is described with the help of two parts: translation and reflection. So in here, as you know, reflection has taken place along z-axis because we see z coordinate with changed signature, and then the transformation has taken place along x-axis, and half means that half of the lattice parameter, which is a in here, if we have half of if we have a, the magnitude of the lattice parameter, then the magnitude of the transformation is half a. Okay. And as far as the subtypes of this glide symmetry operation are concerned, we can have a glide, that is translation by half a, and then translation by half b, designates b glide, and then translation by half c. This designates c glide. But remember, this is very important, my students. A glide never ever doesn't mean that the transformation or the translation happens along a-axis. This doesn't mean like that. This transformation of magnitude half a may happen along b-axis. This may happen along c-axis. This may happen along facial diagonal. This may happen along body diagonal. But if the magnitude of translation or transformation is half a, then that would be a glide. Similarly for the b glide and c glide. As far as the n glide is concerned, then this is the translation by half b plus half c in any direction again. And this n glide, okay, this is perpendicular to a. Okay, the direction, the mentioning of direction is important in here. This glide, the translation direction should be perpendicular to a. The translation direction should be perpendicular to b, and then c. So this should happen in the AB plane in any direction, but in this plane, AB plane, this should happen okay, in the AC plane in any direction. This should happen in the BC plane in any direction. There is another end glide which is specifically related to cubic and tetrahedral structures only. Okay, in this case, translation of half A plus half B plus half C happens. Okay, and this is in a sense body diagonal. D glide, D is derived from the term diamond, okay, and this sort of glide takes place along A plus minus B over 4. This should be the magnitude, or this should be the magnitude, and the magnitude. So this 1 over 4, the quarter, is very important, and because of this quarter we say that this is D glide, the diamond glide. And why is so? Because the diamond crystal structure consists of phase cubic structure such that the two phase cubic structures are drifted apart along the 1 direction by 1 over 4 of that. That is why this D is used in here. Screw axis is another combined symmetry operation. As you see, we can have a rotation and then translation. And first read this text. This symmetry operation is a rotation of 2 pi by n. This is a rotation, and n decides the value of the 4, plus a translation along the axis of rotation by 1 over n. And this is right-handed screw, and if it is left-handed screw, okay, this is quite clear, right-handed, okay, the rotation should be towards right, and if this is towards left, then that would be left-handed screw. But the only difference is we should use a negative sign with that. These are the matrix representations. If the rotation the translation happens along z-axis, then we can have translation along z-axis, and this sort of representation should be used. We can have a translation along y-axis and a translation along x-axis. As far as the rotation is concerned, then we can use that particular value of the theta. These are the types and the corresponding symbolic representations of the screw axis. If we have a 2f screw axis, the value of n is 2, then that would be 2, and in the subscript we will use 1, and this is the crystallographic symbol. If we have a 3f screw axis, then 3, 1, 3, 2 are the two types for that with their corresponding symbols. Similarly, we can have a 4f screw axis, 4, 1, 4, 2, 4, 3, and then the corresponding symbolic representations. Similarly, for the 6f screw axis, we can have these symbolic representations and the values. This is a classic example of a screw axis rotation. The magnitude of rotation is 120 degree, such that the initial coordinates of the point are x, y, and z, and the magnitude of translation along z-axis is 1/3 of the lattice parameter. Then we can use x prime, y prime, and z plus 1/3, right? Now, very important point group. How we can define a point group? this is a set of symmetry elements, and we discussed symmetry elements. These are rotations, reflections, and inversion. These are specifically mentioned in here because these are the rotations that leave a central point fixed while moving other directions and faces of the crystal structure to the positions of features of the same kind. If any unit cell is rotated along a point such that it regenerates itself, okay, then under this operation we can discuss rotations, reflections, and inversion, and then we can have a proper symbolic representation for that. Shortly we are discussing that. For a crystal structure, the group must be consistent with 3D translational symmetry of the lattice. Remember, since we have infinite number of choices to define a unit cell, okay, this is an important sentence that I stated in the start of my presentation. So if this is the case, then we can have infinite number of unit cells, right? Then the point can be raised that why do we consider 32 point groups? Why not infinite? The thing is, the answer lies in this second point. For a crystal structure, the group, the point group must be consistent with 3D translation and symmetry of the lattice. All point groups of the crystal lattice, they don't describe full symmetry of the crystal lattice in 3 dimensions. That is why we ignore all of them except those who describe 3D crystal symmetry of the lattice, and in doing so only 32 point groups come out. Let me read this text for you. There are infinite number of 3D point groups, as I stated earlier. However, due to crystallographic restrictions, they are reduced to 32 point groups. So a space group, this is quite clear from the term space. We move, we translate. Periodic crystal lattices have lattice symmetry involving translation, point symmetry involving rotation and reflection but no translation, and glide and screw symmetry that are combined symmetry operations. We can have in this translation plus rotation, translation plus reflection, translation plus reflection and translation plus rotation. So partly translation is involved in these two combined symmetry operations. So a set of all these symmetry operations constitute a space. Students, these directions are very important for the 7 basic crystal systems. They are very important indeed, though we have discussed it in the classroom, but you need to refresh, to recall all of these directions, because these directions give you full symmetry of their corresponding crystal lattice. For the triclinic structure, we don't have any direction, okay, and the corresponding point group is, this is a 1 bar or 1. For the monoclinic crystal structure, we have 2 or 2 bar. These types of to 2-fold symmetry axis or 2 bar fold symmetry axis, which is parallel to 0, 1, 0. 0, 1, 0 basically is the B axis, okay, and which is parallel to the 2 or 2 bar, and this describes whole symmetry of the crystal. And this is the corresponding symbol 2 over M, 2 and M. 2 over m, 2 and m. So 2 over m means these are parallel to these are perpendicular to each other. Sorry, not parallel. These are the mirror plane in the monoclinic crystal structure. Okay, this is perpendicular to the 2-4 axis of symmetry. We can represent it with 2-4 axis of symmetry only, and we can represent it with m. Similarly, for the orthorhombic crystal structure, we can have 2 over m, 2 over m, 2 over m. Okay, we can have 2 mm. Now in here, this 2 is parallel to. If there is no over, like the slash, then it means that the 2-4 axis of symmetry is parallel to m, and this is parallel to m again. And we can have 2, 2, 2. Okay, I mean these are perpendicular to each other with no mirror planes. We have lost mirror planes in this case. Okay, this 2, remember, this 2 is parallel to m. Okay, and again parallel to m. For the tetragonal crystal structure, we can have, as I mentioned, we should consider the maximum fold symmetry, and the number in here is 4. So 4R4 bar is parallel to C. Okay, and 2 and R2 bar parallel to A and B, and 2 and R2 bar parallel to 1, 1, 0. This is the facial diagonal direction. This is the symbolic representation for that. 4 over m, 2 over m, 2 over m. Okay, 4 is perpendicular to m, 2 is perpendicular to m, 2 is perpendicular to m. Sometimes only 4 over m, sometimes 4 bar, 4, 2, 2, etc. Similarly, for the trigonal crystal structure, we can have 3-4 axis of symmetry, and the 2, we can have a 2-4 axis of symmetry as well, which is parallel to A and B, and 1 bar, 0. We don't have any priority, any choice, any description for the tertiary direction. Okay, in this column, as you see, we are discussing the primary direction, the secondary direction, and the tertiary direction. We don't have any tertiary direction for the trigonal crystal structure, because the crystal symmetry and of course the lattice symmetry is fully described with that. Symbolic representation, 3m. Okay, the m is now 3 and m, they are parallel to each other. 3m, this is 3 bar m, that are parallel to each other. 3m, they are parallel to each other. 3, 2, they are perpendicular to each other, and then 3 bar and 3. For the hexagonal crystal structure, this is the primary direction, which is 0, 0, 1, which is the C axis, such that the 6-4 axis of symmetry is parallel to this. And we can have 2 or 2 bar parallel to 1, 0, 0, 0, 1, 0, and 1 bar, 0. And we can have a tertiary direction as well for the hexagonal crystal structure. We can have 2 and R2 bar parallel to 1 bar, 0. And these are the symbolic representation. 6 over m, they are perpendicular to each other. 2 over m and 2 over m. Okay, these are the point groups. For the cubic structure, we can have a direction which is along A, or along B, or along C, and 3 and R3 bar parallel to 1, 1, 1. We can have for the tertiary direction 2 and R2 bar parallel to phase diagonals, and symbolic representations. Now we will discuss parts of space group. Space group symbol consists of, I will say, at the most 4 parts. at the most 4 parts. We may have 3 parts, we may have 2 parts, but at the most we can have 4 parts of a space group. The first part represents the Bravais lattice type, and the Bravais lattice type is the beginning characteristic of the space group. This may be P, A, B, C, F, I, R. P means primitive. If this is A, which is not very common, this would be A-centered. Again, not very common, but if you see it, then that would be B-centered and C-centered. These 3 are not very common in crystallography. This is very common. F, which is face-centered. I, body-centered. R, which is specifically related to the rhombohedral crystal structure. And then symbols denoting type and orientation of symmetry elements. This part is explained in the next slide. For example, we can have a symbolic representation of a space group which is P63 over MMC. Students, as I stated earlier, the first characteristic is the Bravais lattice descriptor. P stands for primitive. The type of the unit cell in this crystal lattice is primitive. This is the second part. And this part lies along the primary direction. Okay. And the third part is along secondary direction, and this C, which is the diagonal, as we discussed earlier, lies along the tertiary direction. So this means primitive, the first part. The second part is screw axis, which is 6-3 and which is parallel to A. I mean, the translation that is taken place in this screw axis symmetry operation is along A, and A is the secondary direction. Sorry, this is the primary direction. Okay, A is the primary direction. Mirror plane M is perpendicular to A, as I told you earlier. And this amber color again represents a mirror plane which is parallel to B. And then the C glide, and in this C glide the translation is along C axis. Broadly, we can categorize all of the space groups into 2 sections. Semorphic space groups, these are the ones in which no translation is involved. And non-semorphic space groups, they are the ones in which translation is somehow involved. Like 1 bar. In 1 bar we don't have any translation. In rotation we don't have any translation of the unit cell. No translation, no translation. The classic examples are P222 and F23, and similarly IMMM. And the number of these types of space groups is 73. And then we have symmetry operations with translation. Their number is 157, and these are some of the examples: PBCM, PNMA, P4 or MBM. Now, how to convert a space group into its corresponding point groups a very simple technique is involved. The first step is we should remove the symbol for the Bravais lattice, but not whether it is primitive or centered. This is just for your note. Just note it, the Bravais type of that unit cell, and then you should remove it, and then replace symbols for screw axis with the rotation axis nm to n. If you have any general symbol like that, then you should immediately ignore this m and consider this n, and then replace symbols for a glide plane with a mirror plane a, b, c, d, n. If you have these types of symbols, then you should be considering m. This is very important to mention. Don't confuse this n, okay, with this n, right? This is the glide, n glide, but this is the n-fold symmetry. You should differentiate between the two. And these are very beautiful examples giving you a very simple conversion methods. In the first step, you should remove sec p, and we have noted that the type of the unit cell is primitive, so we are left with 6 3 over mmc, and then we have considered 6, and then rest of the symbols are similar. This is 6 mmm, pnma, nma with no p, and then mmm, because this is a glide symmetry, and again a glide symmetry, and are replaced with m. Similarly, these and these, hopefully you have got them. Now, how we can make an educated guess from any space group about the unit cell that it represents? If the secondary the secondary symmetry symbol will always be either 3 or 3 bar, then that would be cubic. The secondary symmetry symbol is like in here. This is the lattice descriptor, the first symmetry symbol, and the second symmetry symbol. Lattice descriptor, the first symmetry symbol, the second symmetry symbol. Lattice descriptor, the first symmetry symbol, and the second symmetry symbol. If this is 3 or 3 bar, then that will be cubic. If the primary symmetry symbol is 4 bar, 4 1, 4 2, 4 3, like 4 is involved in any way, then that would be a tetragonal crystal structure. Lattice descriptor, first or primary symmetry symbol, first or primary symmetry symbol, and so on. For the hexagonal, if the primary symmetry symbol is 6 bar, 6 1, 6 2, 6 3, 6 4, 6 5, 6 is involved in any way, then P6 3 over MCM and P6 MM. The primary symmetry symbol in this case in the trigonal crystal structure is always either of 3 bar, 3 1, 3 2, okay, and then R3C, R3 bar C, P3 1 2, etc. For the orthorhombic crystal structure, the identification is that all three symbols following the lattice descriptor will be either mirror planes, glide planes, 2f rotation, or screw axes. Like in this case, this is the lattice descriptor, and we have a mirror plane, a glide plane, and a screw axis. A glide plane, a mirror plane, and a screw axis. A glide plane, and a mirror plane. If this is the case, then yes, that would be an orthorhombic crystal structure. For the monoclinic, following the lattice descriptor, we will be having a mirror plane, a glide plane, or a 2f rotation. and axis or plane symbol, for instance 2 1, which is the screw axis, and N, okay, a glide plane, and then following the lattice descriptor, a glide plane, following the lattice descriptor, and a 2-fold axis of symmetry. For the triclinic, we can have 1 or 1 bar. So in the concluding remarks, I can say that expertise of symmetry, point group and space group is essential for successful crystal structure determination, and improper consideration of the structure and space group causes serious errors in identifying the correct crystal structure. Pakistan, Zindabad.